Welcome to the moon, a barren, lifeless wasteland. Or so we thought.
It seems like this ancient surface, just craters, it's all been dead, nothing has changed for billions of years. But in reality, it's far from that.
The moon was born in violence and grew up more like a planet than a moon.
The early moon was very much like a planet like the Earth or Mars or Venus is.
Could the moon have once been home to life?
It's not actually a crazy thought to think of the moon as potentially having been a place where life could have existed.
The moon's incredible history makes it more like the Earth than we ever imagined.
It's very reasonable to consider the Earth-Moon system as a pair of twin planets.
Is the moon Earth's cosmic twin? In 2018, we investigated one of science's greatest mysteries, the origin of the moon. It's been a riddle since the Apollo astronauts made a surprising discovery.
Weather's really tricky working on this slope and this soft material. Sure is.
Rocks from the lunar surface reveal that the composition of the moon and Earth are very similar. The two worlds are essentially twins. But how is the moon made of such similar stuff as the Earth?
When we look at other moons, they're not made of the same materials as their planets. And so something different happened here to make our moon and its distinct characteristics.
To discover how the moon and Earth are so alike, we need to go back to the violent early solar system.
The early solar system was incredibly smashy. Things were just running into each other. Objects that had formed were broken apart, reforming. It was a chaotic inner solar system.
Out of this chaos, planets formed, including the Earth. But the violence wasn't over.
As the Earth is forming, it's still being bombarded by all the leftover debris in the solar system. And so it's constantly being impacted.
Small rocky debris bombarded our young planet. But there was an even greater threat to the young Earth. Small protoplanets also orbited the sun. One was on a collision course with Earth. 4.5 billion years ago, a 4,000-mile wide protoplanet called Theia hit the Earth. The impact was only a glancing blow, but the collision still blasted over 81 million trillion tons of debris into space.
In the classical view of how the moon formed, something the size of Mars has a glancing collision with what would have been Earth, thrown off a bunch of material that built a big disk of debris out of which the moon formed.
But there's a problem with this theory. The planets in our solar system are all made of different ingredients. The ingredients change depending upon where the planet is created. Think of the different planets as barbecue sauce.
It's kind of like if you had a barbecue that was vinegar-based, you'd go, oh yeah, that's North Carolina. But if you have it and it's more of a thick red sauce, you go, oh sure, St. Louis.
We have a similar situation in the inner solar system where You know, the various rocks that we're made from here on the Earth, on Mars, the Moon, are all roughly the same kinds of things, but the flavors of the atoms that make up those minerals can be slightly different.
The unique flavor of each planet is created by different types of chemical elements. Mars has more oxygen-18 than the Earth. Venus has less argon-40. Each world has a distinctive mix of ingredients, a signature sauce. So what about the Moon?
If the Earth is different from Mars and Mars is different from the asteroids, we might expect that Theia, the object that ran into the Earth, should have had this different composition flavor than the Earth.
When Theia collided with the Earth, the impact blasted trillions of tons of material into space. But a glancing blow would cause more damage to Theia. So most of the ingredients that make up the Moon should have come from Theia.
And that would show up today in the composition of the Moon.
But it doesn't. The Earth and Moon are made of very similar ingredients. So the glancing impact theory could be wrong.
The way to potentially solve the issue of the similar compositions and flavors of the Earth and Moon is, as a result of the impact, they really mixed up their materials very well together. And so they're similar composition today because of how well they mixed.
New research from planetary formation expert Professor Sarah Stewart suggests Theia didn't just hit Earth with a glancing blow. It smashed into our planet head on.
Our model for the origin of the Moon still begins with a giant impact. The energy of the impact generates a shock wave that travels through both objects. That shock wave deposits enough energy to melt and partially vaporize both bodies. But now we know that giant impacts make a new astronomical object called a synestia.
A synestia is a donut-shaped, spinning ring of molten and vaporized rock. The impact that formed it released so much energy, the synestia could have glowed as bright as the sun.
The surface of the structure that you observe would be magma rain clouds. And so it would be glowing orange hot, and it would look like a swirling ball of gas.
The cloud of material swirled for hundreds of years, with the remains of Theia and the Earth inside, like ingredients in a planetary cocktail.
Everything mixes together and you form a huge cloud of material. So it's not as simple as building a small disk and building the Moon.
Gradually, the synestia cooled and the donut-shaped cloud shrank. Rock vapor condensed into a liquid, then solid rock. Earth began to reform.
And it didn't recondense into a single, more massive Earth. Instead, there was enough material at the fringes of this blob to condense into its own object, which became the Moon.
Earth took the lion's share of material. The Moon lived off scraps. But it did grab enough material to slowly emerge from a hail of molten rock.
You would have had two really hot, mostly molten bodies in really close orbits to each other.
If you were a Martian during the time of the young Earth and Moon, 4 billion years ago, when you look back at the Earth and Moon, it would have looked like a double planet to you.
And because the Moon and Earth formed together from a synestia, their chemical compositions are almost identical. But some things were very different. The Earth got much more water than the Moon.
If the Earth and the Moon formed out of the same materials, then why is the Earth covered in oceans while the Moon is bone dry?
Clues may be found in the way the Earth and Moon grew from the materials in the synestia. The spinning donut of debris contained more than just rock. It was filled with volatile materials like vaporized water and carbon dioxide gas.
As this debris disk started to kind of coalesce, it formed these really high temperature cores that were the Earth and the Moon. But it was still too hot for the volatiles to be able to condense.
Over time, the synestia cooled enough for the Earth and Moon to capture the volatile gases. But most of the gas was pulled in by the Earth's powerful gravity.
When the Moon separated from the synestia, most of the water in the atmosphere stayed in the gas that was trapped by the Earth.
The only materials left behind to coalesce onto the Moon that were volatile were just a little bit of water. And we can see evidence of that water today in the lunar soils. The rest of the water was attracted to the much more massive Earth.
The volatile gases and water were captured by the Moon and Earth and became trapped in the oceans of molten rock that covered the two worlds. But the similarities of the twin molten worlds were more than skin deep.
Similar to the Earth, the Moon, just after its formation, would have been very, very hot. You would have had a really hot, molten body solidifying at the surface, building a crust, and solidifying from the outside in.
As the Earth cooled, an atmosphere formed and life evolved. New lunar data suggests the Moon may have followed the same path. Was the Moon once home to life? In 2018, planetary scientists were hunting for clues about the Moon's violent past. They studied maps from the Lunar Reconnaissance Orbiter and focused on dark patches of the Moon known as the lunar seas.
The names we use for features we see on the Moon's surface are things like Sea of Tranquility.
And so before we knew what they were, astronomers would look at this and say, well, they look like oceans and seas. And that's what they called them. Mare means sea, and so you have Mare Tranquillitatis, which is the Sea of Tranquility.
But they're not seas of water, they're seas of lava.
Over 3 billion years ago, the Moon was covered in vast lava seas, fed by giant eruptions of magma.
These patches that we see on the Moon were lava eruptions which have filled in these basins. These are hundreds of miles across. These are enormous, much larger than even the biggest volcanoes on Earth.
If you were standing on the Earth 3.5 billion years ago, you'd probably see the glow of the individual lava flows flowing out across the surface of the mare.
We can work out how much lava flowed across the Moon by measuring the lunar seas. But that's not all. The amount of lava in the seas can tell us if our planetary twin had an atmosphere.
Volcanoes on Earth actually don't just spew out lava. There's outgassing. Literally gas underneath the Earth comes out as well. And you get sulfur gases and carbon monoxide and a lot of other things. Well, the same thing happened on the Moon as well.
The ancient lunar lava flows revealed that the Moon's surface was covered in lava for hundreds of millions of years. The biggest eruptions happened around 3.5 billion years ago. They covered the Moon in 200,000 trillion cubic feet of lava.
We estimate there was enough lava produced to cover the entire continental United States to a depth of 1/4 mile in lava.
Roughly 3 billion cubic feet of lava gushed out of the moon's volcanic fissures every year. These massive eruptions also spewed out around 10 trillion tons of gas, including water vapor and carbon monoxide.
It would be kind of a hellscape of erupting lavas. And then noxious gases would be spewing out of volcanoes. So all of this eruption of vast amounts of lava probably would have created an atmosphere around the moon.
It's still pretty thin compared to Earth's atmosphere, but maybe something on the order of maybe 1.5 times the density of Mars's atmosphere today. There may be just enough pressure there to be able to keep water liquid on the surface.
With an atmosphere in place around the moon, water vapor condensed into pools of liquid water. The thin atmosphere trapped warmth, preventing the water from freezing, creating a harsh but potentially habitable environment.
3 billion years ago, Earth had life. Is it possible that the moon did too?
This is not something that we have a lot of information about, but it's plausible because the moon certainly had a lot of volcanic eruptions that could have formed an atmosphere. So it is not a crazy thought to think there was a window of time where the moon was habitable.
We think that life needs vast seas and oceans to form. So it's unlikely that life started in the shallow pools of water on the moon. But fossil records show that the Earth had bacterial life when the moon had its atmosphere. Could Earth bacteria have kick-started life on the moon?
If you have a particularly violent impact, you could actually launch a pretty good chunk of rock up into space. And while the surface of that rock would be very hot and exposed to the vacuum of space, the interior could be largely unmodified. So think about there being bacteria in the rock. You know, most Earth rocks are full of bacteria inside. All of a sudden, it gets launched into space and lands on the moon.
The moon seems really far away, right? It's 250,000 miles away. It's a 4-day trip by rocket. So you wouldn't think that the Earth and the moon would have exchanged any material. But when you look at all the physics, yeah, a big enough asteroid impact could blast material off into space. And some of it, at least, would land on the moon.
So given that material could have been going from the Earth to the moon at this time, it may be that the first visitor from Earth to the moon was not Neil Armstrong, but was actually a microbe.
But the warm, wet lunar environment didn't last. When the lunar volcanoes that replenished the atmosphere stopped erupting, the moon's weak gravity couldn't hold on to the atmosphere. In just a few million years, it was all gone. The surface water was lost to space. Temperatures plummeted. Any life died.
Even though the Earth and the Moon started out nearly identical from this same catastrophic collision, as time went on, they grew further and further apart, and they followed different life paths because the moon was small and cooled off. The Earth was large, was able to support an atmosphere, was able to support liquid water. The moon got none of that because it was just too small.
We thought that the moon's size meant its molten interior cooled quickly, killing the volcanoes and stopping the core from generating a magnetic field. But new research suggests we may have got our lunar history wrong. In 2017, we re-examined 1-billion-year-old lunar rocks collected by the Apollo 15 mission and discovered something strange. The rocks had evidence of a lunar magnetic field, billions of years after the moon's magnetism should have disappeared.
We've got a little bit of a mystery here. When the moon was molten, it could support a magnetic field. But the moon cooled off, and when it solidified, it should have shut off quickly its magnetic field. But samples from the Apollo mission revealed that the magnetic field hung on longer than what we think it took for the moon to cool off.
We thought the moon lost its magnetic field 3 billion years ago. But the Apollo 15 rocks showed the moon had a magnetic field just 1 billion years ago. To explain this discrepancy, we must look deep inside the moon and back in time. 3.5 billion years ago, the hot liquid core in the center of the moon rotated, generating a magnetic field.
So early in the history of the Earth and the moon, both would have had molten cores capable of generating magnetic fields.
But the moon is roughly a 50th of the volume of the Earth. And this size difference had a major impact on the moon's interior.
While the moon and Earth may have had a common origin, they've evolved in very different ways. The moon, being a much smaller body, actually loses its heat much faster than the Earth.
So while they both would have had magnetic fields, the Earth's still persists today. The Earth's core is still generating magnetic field, whereas the moon cooled off and the magnetic field would have dissipated a long time ago in its history.
Magnetic fields protected the early Earth and moon from the sun's solar wind and cosmic radiation.
Without the magnetic field, we would constantly be bombarded by streams of charged particles, harmful radiation from the solar wind. So this magnetic field is really an important guardian shield for us.
The moon's magnetic field should have died 3 billion years ago when the core cooled and solidified. But the billion-year-old moon rocks suggest it didn't.
So the question is, how could the moon have had a magnetic field? And the answer may be that because of tidal forces from the Earth, the moon is being kind of flexed.
When the moon formed, it orbited just 12,000 miles away from the Earth, making it appear 20 times larger in our sky. The moon was so close, Earth's gravity could stretch and flex it. This internal distortion of lunar rock created friction, and friction creates heat.
And it's a lot of friction. It's so much heat dumped into the interior of the moon from this effect that it actually kept the mantle of the moon molten longer than it would have been if it had just been sitting in space.
So it could have prolonged the heating on the internal parts of the moon and extended the time that its magnetic field would have survived.
This heat kept the moon's magnetic field alive for an extra 2 billion years. Long enough to imprint the 1 billion-year-old Apollo 15 rocks with a magnetic field. But over time, as the moon moved away from the Earth, the friction heating dropped. The lunar core cooled.
When the moon was closer, this effect was very, very strong. Nowadays, the moon is far enough away that that effect is too weak to keep the mantle molten.
Eventually, the moon lost its magnetic field when it stopped being so liquid and gooey on the inside. Once it solidifies, once it cools, there's no more movement, and so the magnetic field just falls apart.
When the moon lost its magnetic shielding, it flatlined. The solar wind bombarded the lunar surface, leaving the moon a radiation-scorched wasteland. A dead world orbiting the living Earth. Or so we thought.
In a general sense, it's okay to say the moon is dead. It's just kind of sitting there. What you see is what you get. However, the Apollo astronauts left seismometers on the moon, and what they found is that it's only mostly dead.
Powerful forces are stirring on the moon. The lunar surface is shaking, giving rise to vast new rocky structures. Could our cosmic twin be coming back to life? The moon's surface carries a record of its history. The scars of asteroid impacts show that it hasn't been active for many years. But scans of the Schrödinger Basin tell a different story. They show recently formed rocky ridges free of large craters.
The moon appears to have been dead for a long time, and we can tell because it's scarred by all these craters from impacts for the past 4 billion years. But there's some features on the moon that are free from craters, which means they're relatively young. So how can a dead world have a new young feature?
These young features are called lobate scarps.
They're faults in the moon's crust that are formed by two pieces of crust coming together and sort of one riding over the top of the other.
These scarps can be tens of miles long and hundreds of feet high. Something powerful is creating these rock formations. But what? The answer could be found in a decades-old lunar mystery: moonquakes.
Just as the Earth has earthquakes, the moon, we know, also has moonquakes.
Apollo astronauts left seismometers on the moon to measure moonquakes. And they got some, and that's not terribly surprising because without an atmosphere, any little bit of rock out in space that slams into the moon's surface, it's going to hit and create a shock wave, which will be picked up by the seismometers. But they also picked up something that wasn't from asteroid impacts. And it turns out those were true moonquakes.
Over an 8-year period, the Apollo missions recorded more than 13,000 tremors. 28 of these were mysterious true moonquakes, measuring up to 5 on the Richter scale. These moonquakes can't be explained by events on the lunar surface. But what about underneath it?
Given how small the moon is, you would imagine that it cooled off long ago and it's just an inert rock doing nothing. But something is happening under the surface of the moon. The moon may not be as dead as we thought.
On Earth, our planet's hot interior drives tectonic activity and triggers earthquakes. So, could the moon's interior still move like the Earth's?
Probably the most common mechanism that generates earthquakes is the slipping of our tectonic plates, the cracked crust of the Earth. They don't slide and glide evenly. They get hung up on each other because of friction, and the stresses build, and over time that frictional force will give way, and there'll be a slippage in the plate.
And for that to work, you have to have a real active tectonic system where things are colliding and moving around. You need a liquid mantle that allows this sort of movement.
When we use the Apollo seismometer data to look for a liquid mantle in the moon, we were in for a surprise. The moon's crust is made of solid rock that extends 600 miles beneath the lunar surface. It's 20 times thicker than the Earth's solid crust.
On the moon, there's no crust floating over sort of a liquid mantle. So without that, you're not getting the same sort of tectonic activity that you do on the Earth.
Without a liquid molten mantle, true moonquakes can last for over 10 minutes, many times longer than quakes here on Earth.
On the Earth, we've got plenty of things to absorb all that energy from earthquakes. We've got liquid mantle or molten mantle, liquid oceans, a lot of shock absorbers. On the moon, a big solid rock that's more or less dry as a bone, that energy can just ring and ring and ring and continue for a long time.
Moonquakes last a lot longer than earthquakes simply because the interior of the moon is mostly rigid and dense. It's dense all the way down to about 600 miles, whereas on Earth, we start getting sort of gushier material at about 100 miles deep. So if you have 600 miles of rigid material, then the waves can be transmitted through that really efficiently.
Earth-like tectonic activity didn't trigger the moonquakes, so we looked for something else. By triangulating the tremor's epicenter, we discovered that they originated around 15 miles underground. And one of the quakes happened near the Schrödinger Basin, where we found the lobate scarp ridges.
The lobate scarps are evidence probably of the sources of the shallow moonquakes that we're detecting with the lunar seismometers left by the Apollo missions.
Let's put the evidence together. Something formed the lobate scarps, set off giant moonquakes, and it's happening inside solid rock.
How in the world is that possible? It turns out the moon is shrinking. It's shrinking as it cools.
If you take something that's cooling like that, it's going to try to shrink. And the surface of the moon is shrinking, but it can't. It can't physically shrink. It puts it under too much pressure, and at some point, it's going to snap. And that's where we think these scarps are coming from. And if you create a scarp like that, you're gonna get moonquakes.
The new ridges and moonquakes aren't the signs of a healthy, tectonically active world. They're the moon's death rattle. Our cosmic twin is dying, but this may have an upside for humankind. The dead moon can warn us about threats that the living Earth can't. And it looks like Earth is getting more dangerous. January 2019. We studied data from the moon to discover the true risk of asteroids hitting planet Earth.
When you look at the Earth, you don't see a lot of impact craters, and you might think, asteroid impacts don't happen that often. And then you look at the moon and go, it's covered in impacts.
On Earth, weather, volcanic activity, even life wears away and obscures craters. So it's hard to assess the danger facing our planet. Studying the moon is easier.
A cool thing about the moon is that without erosion on its surface, without an atmosphere, without water, without tectonic activity, anything that ever hit the moon leaves a record behind.
And because the Earth and moon orbit together, similar numbers of asteroids hit both worlds relative to their size.
So we can look at the moon the same way we can look at tree rings inside of a giant tree. We can see what the past was like.
The scarred lunar surface reveals how many asteroids hit the moon and Earth in the past. But to know the current risk of a strike, we need to know when these asteroids hit. Clues are hidden in the rocks and dust around the moon's impact craters.
One of the natural outcomes of excavating a impact crater is to eject and move that rock and push it onto the surface surrounding it. So you get ejecta of all kinds around any impact crater.
The moon's craters remain unchanged for billions of years, but ejected rock erodes over time. The cause? Tiny asteroids around the size of a grain of sand rain down onto the moon at thousands of miles an hour and erode the ejected rocks.
On the moon, that's the main means of weathering, where these little impactors come and they just break up rock over and over and over again until you end up with this fine regolith powder.
We can use this slow erosion of rock into regolith to figure out when impacts happened.
We can get a rough estimate of the dates by just looking at how many rocks, ejecta blocks there are around a big lunar crater. A young crater is going to have a lot of rocks around them. As that crater ages, the amount of fresh ejecta blocks around a crater will start to degrade. So older craters, you might expect to have a lot fewer ejecta blocks than younger craters.
But satellites don't have the resolution to see the ejecta around the craters directly. So we use a clever trick. We compare the temperature of the ejected rocks in the heat of the day and during the cold lunar night.
Little objects will tend to cool off much faster than larger objects. And so a big lunar boulder will retain the heat from its daytime exposure to the sun a lot longer than the individual little grains in the lunar soil.
Analyzing the temperature of rocks around the moon's craters reveals an alarming pattern.
We would think that over time, there would be less and less material floating around the solar system to hit the moon. But yet, there seems to actually have been an increase in impacts in about the last 300 million years.
An increase in impacts on the moon means an increase in impacts on the Earth. We are now experiencing 3 times more impacts than we were 300 million years ago. So why the sudden increase?
What we think we're seeing today with this increased rate of impacts on the Earth-Moon system is the evidence of a relatively recent large breakup event in the main asteroid belt. If you break up, catastrophically disrupt an asteroid in the main belt due to another asteroid running into it, that's going to create a shower of asteroid debris raining through the inner solar system for the millions of years after that impact.
Roughly 300 million years ago, a shower of rocky debris started slamming into the Earth and Moon. On the Moon, the impacts created dozens of large craters, some over 50 miles wide. The Earth suffered thousands of large impacts. Some of the asteroids may still be hurtling our way.
So clearly, the solar system is a dangerous place.
We should be concerned about asteroids because as far as cosmic dangers go, they're #1 on the list. And it doesn't have to be some huge planet-sized thing to cause some serious damage. Exploding over a major city or off the coast near a major city could wreak horrible devastation. It could flatten a city.
In the fight against asteroids, forewarned is forearmed. So any information the moon can give us helps our cause. The moon is helping humankind today, but in the future, it could cause the end of the world as we know it. The moon and Earth have been companions in space for 4.5 billion years. They grew up together, but a strange feature of the moon's orbit shows the relationship is getting stretched.
You might think that the moon simply orbits the Earth. It's going around the Earth, and that's it. It's not really the case.
In our solar system, the moon is an oddball. It's huge compared to our planet.
Most of the moons in the solar system are much, much smaller than their host planets. So if you look at the moons of, even the largest of the moons of Jupiter, are minuscule in size compared to Jupiter itself. The moons of Mars are mere fleas circling an elephant in that regard. Our moon is relatively big. It's the biggest moon in the solar system relative to the size of the planet.
So the Earth pulls on the moon, but the moon's pulling on the Earth too. It has gravity. So really what's happening is it's not just the moon going around the Earth. They're both going around their center of mass, their center of gravity.
Each body in the system orbits the center of mass of the system, and we call that location the barycenter.
If the barycenter lay outside of the Earth, the moon would be a binary planet with the Earth. But right now, the barycenter is about 1,000 miles beneath our feet.
By that definition, the Earth-Moon system isn't quite a binary system. It's close, but that barycenter, that common center of mass, is inside the surface of the Earth.
The location of the barycenter is affected by the distance between the two worlds. So while the moon and Earth aren't a binary system today, they might be in the future. Every day, the moon gets farther away from the Earth, and the barycenter moves closer to the Earth's surface, thanks to the gravity of our planet's oceans.
If you live anywhere near a large body of water on our planet, you're aware of the daily tides. The ocean levels rise and then they retreat.
The moon's gravity pulls on our planet's water, creating tides. But the Earth's spin pushes this bulge of tidal water ahead of the moon. There is so much water in the tidal bulge that it has its own gravitational pull. It tugs on the moon, speeding it up and moving our cosmic twin into a higher orbit, farther from the Earth.
Every day it swings a little bit farther away from us, and it goes about 1.5 inches per year farther away. That's about the rate that your fingernails grow.
Predicting the moon's movements into the distant future is extremely difficult. But if it continues to move away at the current rate, the barycenter will be outside the Earth in less than 4 billion years. The Earth and Moon will become a binary system. But that's not the end of the story. As it swings further away, the moon drags on the Earth, slowing our planet's rotation and lengthening our days.
And if you ran that forward in time, eventually we could reach a point where the Earth's day is equal to the moon's orbit, and one face of the Earth always faces one face of the moon. And we call that a tidally locked configuration.
When the Earth tidally locks to the moon, a single day on Earth will last over 600 hours. Long, hot days and freezing cold nights could whip up massive storms across the planet, or trigger a runaway greenhouse effect, leaving the Earth a boiling furnace like Venus, all because of the moon.
We're so used to describing ourselves as Earthlings. We live on the planet Earth. But actually, we live in an Earth-Moon system, and the moon has been affecting us ever since the beginning of our planet.
Earth would not be Earth without the moon. The moon affects so many processes that are happening on Earth. We would be a completely different planet.
The Earth and Moon were born as twins. They took different paths, but their stories remain entwined.
The record of crater activity, the relationship between the moon and the tides, the formation of the moon itself, all the tremors and activities happening deep in the core of the moon, despite the fact that it's cold and dead, confirm that, the moon really is one of the most interesting objects in the solar system.
Our lunar companion is more than just a moon. It's a whole world of its own, with its own rich history. The moon is the Earth's cosmic twin.